Hey guys, today we are going to talk about horizontal asymptotes, vertical asymptotes, and holes a little bit more. So, a couple of days ago, we started with horizontal and vertical asymptotes, but we were doing it in transformation form. So, today we're moving forward and we're looking at some of these equations that may look something like this, where it's not in transformation form for us. So we're going to start with holes in vertical asymptotes. These are going to be called discontinuities because anywhere that there's a hole or a vertical asymptote on the graph, it is causing a break in the domain. So if you think back to Unit 1, domain is just all of those possible x values. So whenever you have a hole or a vertical asymptote, that means x doesn't work at that point. So to find discontinuities or holes or vertical asymptotes, what you're going to do is you're going to factor, there we go, factor each denominator. And then once you have the denominators factored, you are going to set them equal to 0 and then solve for x in each of the factors. So whenever I say common factors, that means the same factor is in the numerator and the denominator. And so those are going to cross out. So if you have a factor that crosses out or cancels out because it's in the numerator and denominator, that's going to represent a hole at that point. And then factors that don't cancel out are going to represent vertical asymptotes. So if you haven't gotten these notes down yet, go ahead and pause here so that you can make sure you get all of this information written down on your paper. So now we're going to do an example where we have to find all of the holes or vertical asymptotes. So I have this rational equation, and then the first thing I'm going to do is I'm going to go ahead and factor. I'm going to factor the numerator and denominator, but remember that it's the denominator that's giving you these holes or vertical asymptotes. So the reason for that is because whenever you factor and you set the factor equal to 0 and solve, that's causing there to be a 0 in the denominator, and anytime that there's a 0 in the denominator, you would be dividing by 0, and you can't do that. So that's why you're focusing on the denominator for these. But we're going to go ahead and factor x squared plus 3x plus 2 and x squared minus 1. So for the x squared plus 3x plus 2, you're looking for two numbers that multiply to 2 and add to 3. So those two numbers are going to be 2 and 1. So for those two factors, you would have x plus 2 and x plus 1. So then for the denominator, x squared minus 1 is a special case that's called a difference of perfect squares, where anytime that you have an x squared minus a perfect square, like 1 or 4 or 9 or 16 and so on, then your factors are going to be x plus the square root of your perfect square times x minus the square root of your perfect square. And so in this scenario where we have x squared minus 1, we're going to have x plus the square root of 1, which is just 1, and x minus the square root of 1, which is still just 1. So then we're going to look at these and we can cross out common factors. So we have an x plus 1 in the numerator and denominator. So that means we can cross that out. So the x plus 1 factor is going to give us a hole. So what we're going to do to find out where that hole is we're going to set x plus 1 equal to 0. Then we're going to subtract 1 from both sides to solve for x, and you get that x equals negative 1. And so the way that we would word that for our answer is that we have a hole on the graph at x equals negative 1. And then the leftover factors in the denominator, that's going to lead to a vertical asymptote. So our x minus 1 is going to give us a vertical asymptote. And I'm just going to abbreviate that with VA. So we're going to set x minus 1 equal to 0, add 1 on both sides, and we would get x equals 1. And so that would be a vertical asymptote at x equals 1. So then we're going to go ahead and do another example. So in this one, we have x on the top. X can't be factored down into anything simpler, so we're just going to leave that x as our numerator. And then we have x squared minus 1 as our denominator, which we already factored on the last slide into x plus 1 and x minus 1. So now if you look at this one, nothing cancels out in the numerator and the denominator. So that means that both of these factors are going to be vertical asymptotes. So I'm going to go ahead and set both of them equal to 0. And then for the x plus 1, I'm going to subtract 1 on both sides and get x equals negative 1. And for the x minus 1, I'll add 1 to both sides and get x equals positive 1. So for this one, since they're both vertical asymptotes, you can write that you have a vertical asymptote at x equals negative 1 and x equals positive 1. And that would be your answer whenever you're finding all the holes and vertical asymptotes on that one. So then here's another example. So we have f of x is x squared minus 4 over x plus 2. So our denominator of x plus 2 cannot be factored any further. It's going to stay x plus 2. And then our x squared minus 4, that's another scenario where it's a difference of perfect squares. So we're going to have x plus the square root of 4, which is 2, times x minus the square root of 4, which is 2. And so now I notice that the x plus 2 in the numerator and denominator cancel. So that means we're going to have a hole at that factor. So we're going to set x plus 2 equal to 0. To solve for that, I'm going to subtract 2 on both sides, and I'll get x equals negative 2. And so that's going to be a hole at x equals negative 2. And then there's not any more factors in the denominator, so this is going to be our whole answer. There's just a whole x equals negative 2. We don't have to worry about the x minus 2 in the numerator because you only worry about the factors that are in the denominator whenever you're finding the holes in vertical asymptotes. So for this one, you just have a hole at x equals negative 2. And then here is our last example, and it's basically just the reciprocal of what we just did. So we're going to have the x plus 2 on the top, and then we already factored that on the last slide. It was x plus 2 times x minus 2. And then the one that cancels is still going to be our x plus 2. So there's still going to be the same hole at x equals negative 2 as there was on the last problem, because you would set that x plus 2 equal to 0 and subtract 2 from both sides. So then you also have this x minus 2 though. So we're going to set the x minus 2 equal to 0, and this one is going to give us a vertical asymptote because that's a leftover factor in the denominator that doesn't cancel out with the numerator. So then I'm going to add 2 to solve for that factor, and I get x equals positive 2. And so there would be a vertical asymptote at x equals positive 2. So for this problem, your answer would be that there is a hole at x equals negative 2 and a vertical asymptote at x equals 2. And you would need both of those for your final answer. So the main things to remember for finding holes in vertical asymptotes is always start with factoring, and then whatever cancels out with the numerator and denominator, remember that that factor is going to give you a hole. And then if you have a factor left over on the bottom, like in the denominator, then that factor is going to give you a vertical asymptote. So now we still need to talk about horizontal asymptotes, which I will tell you that most people find horizontal asymptotes to be a little bit easier than finding vertical asymptotes. So what we're going to talk about is to find horizontal asymptotes, what you're going to do is you're going to compare the degree of the numerator and denominator. And remember just that the degree is going to be the highest exponent. So that's what you're looking at, is the highest exponent in the numerator and the highest exponent in the denominator. And then if the degree in the numerator is less than the degree in the denominator, so less than, then the horizontal asymptote is at y equals 0. And then I'm going to give you a way to remember these a little bit easier in just 1 second. But then if the degree in the numerator is bigger than the degree in the denominator, then there's not going to be a horizontal asymptote at all. So that would be no HA or no horizontal asymptote. And then if they are the same, then the horizontal asymptote is going to be at the ratio of the coefficients. So just an example of that would be like if you have y equals 2x squared plus 3 over, say, 3x squared minus 1. Then in that case, since your highest degree or highest exponent in both is 2, you would have an HA at the ratio of your coefficients, which is just 2/3. So, and then I don't think I mentioned this before, but for the horizontal asymptotes, you're going to have y equals for your equations. And then for the vertical asymptotes, it was x equals. So just keep that in mind as you're writing the equations. So then the way that I kind of go about remembering these is there's 3 different scenarios. So we have 1, 2, 3. So the first scenario is that the degree in the numerator is smaller than the degree in the denominator. So what we're going to call that is little over big. And then the second is the opposite of that. So the degree in the denominator is smaller, so we would have big over little. And then the third scenario is that you have the same degree. So I would say same over same. So whenever you have a little over big, so the highest exponent in the numerator is smaller than the highest exponent in the denominator, then the horizontal asymptote is going to be at y equals 0. If you have big over little, then that means that there's not going to be a horizontal asymptote at all. So I would say no HA. And then for same over same, the horizontal asymptote is going to be at y equals the ratio of the coefficients. So we're going to do just a couple of examples of like looking at these and kind of just determining what this means. So my first example here, we have 3x squared minus 1 over 2x squared plus 1. So in this one, our highest exponent in the numerator is 2, and the highest exponent in the denominator is also 2. So that means I'm going to use y equals the ratio of the coefficients. And so then if I'm looking for that ratio of the coefficients, I'm looking at these 2 numbers that are in front of the variable with the highest exponent. And so we're going to have y equals 3 over 2 as our horizontal asymptote. So in my next example, I have 3x over x squared plus 1. So if you look at 3x, then the degree on 3x is just going to be 1 because it would be like 3x to the first power. So in that scenario, we have the degree of 1 on top and the degree of 2 on the bottom. So we have little over big, and anytime that we have little over big, we have a horizontal asymptote at y equals 0. And then for my last one, I have a degree of 2 on top and a degree of 1 on the bottom. So that's the scenario of big over little. And whenever we have big over little, we have no horizontal asymptote at all. So the main takeaway for horizontal asymptotes is just going to be to remember these three rules. So again, if the degree in the numerator is smaller than the one in the denominator, you have a horizontal asymptote at y equals 0. If the degree in the numerator is bigger than the degree in the denominator, you're not going to have a horizontal asymptote. And if they're the same, then you just use the ratio of the coefficients that are in front of the variables that have that highest degree. And that's going to be all for horizontal asymptotes.